Hello everybody, welcome to another video. In this video I'm going to be doing a continuation of section 4.2 which is about graphs of exponential functions and their transformations. In the first part of this section that I covered, we did a warm-up example where we matched some graphs of some exponential functions with their equations. These were problems 13 through 18 from the textbook. Then we talked about the toolkit or parent function f of x equals b to the x. Noted the functions were 1 to 1, horizontal asymptote y equals 0, domain all real numbers. Looking at the graphs down here, you can see the range would be 0 to infinity. Those graphs are strictly above the x-axis. Y-intercept of 0, 1, and the graph of the function or the function would be increasing if you have a base bigger than 1 and decreasing if you have a base less than 1. Okay. Went through an example of plotting the functions f of x equals 4 to the x and g of x equals 1/4 to the x power. We saw that those two graphs were related. They ended up being the horizontal reflections of each other, or the graph of one was the reflection of the other over the y-axis. And then we summarized transformations of these parent functions. Okay, and ended with a summary of a general transformation of y equals b to the x with values a, c, and d. C and d are going to account for the shifts left or right, or the value of d is going to account for the shifting up or down. And the value of a is going to lead us to either a vertical stretching or a vertical compression. If a is less than 0, we would follow everything with a reflection about the x-axis. Finished up going through example 2, starting with the parent function f of x equals e to the x. We found a form for the function obtained by compressing the graph of e to the x vertically by a factor of 1/3, reflected over the x-axis, and then shifted down to units. Now, for the one example that I haven't yet covered, we are going to be given the graph of a transformed parent function, and we're going to find its form. And we'll start here by at least a fact, and then describe the steps of how you would find the equation of a transformed exponential function from a graph. So we'll start with the fact above. Every transformation of an exponential function, or the parent function y equals b to the x, can be written simply in the form y equals a times b to the x plus d. So really every transformation of b to the x can be viewed possibly with only 3 transformations. Okay. The value of a is going to tell us if any vertical stretching or compressions have taken place. If a is negative, there is a vertical reflection over the x-axis, and plus d, or the value of d, is going to give us any shifting up or down. And first I want to maybe just explain why there's no need to actually consider any horizontal shifting if we're starting with the graph of a transform exponential function. So you might remember from the previous box above, but the general form of a transformation of b to the x is y equals a times b to the x plus c plus d. Now, a couple facts or reminders on the right is, first of all, if I take b to the x times b to the c power, that can just be simply written as b to the x plus c. So if you multiply two numbers with the same base, you add their exponents. And what that's going to allow us to do is actually to split up b to the x plus c as a, so the function becomes a times b to the x times b to the c plus d. And I'll rearrange this slightly as a times b to the c times b to the x plus d. And right here, a times b to the c, this is just some constant. So whatever a times b to the c is, it's still going to accomplish vertical stretching and compressing, and if it's negative, it's still going to give us a vertical reflection. So what we're going to do is we're just going to replace a times b to the c, since it's a constant, with just a number a. And like I said, any transformation of an exponential function can just be written as a times b to the x plus d. Okay. All right, so it's about splitting up the b to the x plus c power, and then realizing that a times b to the c is still just a constant. Okay, so to reiterate, I took the general form of the transformation of b to the x, and where the horizontal shift was expressed in the exponent with b to the x plus c. Then I used the properties of exponents to separate those powers as b to the x times b to the c. And then in the third step, what I did is I just rearranged the multiplication. B to the x times b to the c is also b to the c times b to the x. And then the constant a times b to the c can again be thought of just as a vertical scaling factor. It's okay to just replace a times b to the c with just a single value of a, and that gives us a much more simplified form of a transformation of the parent function b to the x. Okay, so now what we'll do is we'll do an example. How do I find the equation of a transformed exponential function from its graph? And what we're going to do is we're going to start with the general form y equals a times b to the x plus d. Now we're first going to identify d using the horizontal asymptote y equals d. So it turns out that, again, the parent function, if we go back up to their graphs, has a horizontal asymptote of y equals 0. And after the vertical scaling and reflection, y equals 0 would still be the vertical or horizontal asymptote, So it turns out that just if you shift the parent function up or down, whatever the vertical shift is going to tell you what the horizontal asymptote is, and vice versa. So coming back down to the graph here, I'll just go ahead and draw that in. Okay, so if you guys look, as we move to the left on the graph, I think we can see that the function, the y coordinates are approaching the value of 8 as x goes to negative infinity. And what that's going to tell us, and actually let's just go back here, let's go back to step 1, right? We're trying to find this function, f of x equals a times b to the x plus d. Now number 2, y equals 8 is the horizontal asymptote, and that's just going to tell us that d must be 8. Okay, and then I'll go ahead and replace that value in my general form. F of x would be a times b to the x plus 8. Okay, now number 3 says substitute the coordinates of the y-intercept into the equation and solve for the vertical scaling factor a. And then after we do that, step 4 says substitute the coordinates of any other point on the graph into the equation to solve for the base b. So we only need 2 points on this graph. If you look over to the left, our y-intercept has coordinates, looks like about 0 and 5. And let's see if I can find any other point on this graph that's going to help us determine the value of the base. Now, no other points actually go through where any of the grid lines meet, but I'm just going to estimate another point over here to the left. It seems like when x is negative 3, the y coordinate is 7. So I'm just going to go with that. Okay, now step 3. When x is equal to 0 using the y-intercept, f of x is equal to 5. So substituting that into the equation from step 2, we have 5 equals a times b to the 0 power plus 8. And anything to the 0 power is positive 1. Okay, so this b to the 0 right here, that's just positive 1. So 5 ends up equaling a plus 8, and subtracting 8 from both sides, a has to be negative 3. And we can again go ahead and just rewrite the function. Now that we know a is negative 3, f of x must be negative 3 times b to the x power plus 8. Okay, step 4. So we're going to use the coordinates of that other point on the graph. When x is negative 3, f of x is equal to 7. Okay, and what that implies is that using the equation from the previous step, just so you can see them, after step 2 it was f of x equals a times b to the x plus 8. After step 3, f of x was negative 3 times b to the x plus 8. So using what we have from step 3, f of x was 7 when x was negative 3. So 7 equals negative 3 times b to the minus 3 plus 8. Now from here, we can go ahead and subtract 8 from both sides. So minus 3b to the negative 3 equals 7 minus 8, which is negative 1. And we can divide both sides by negative 3. So b to the negative 3 is going to equal 1/3. Okay. And then I'm just going to raise both sides to the negative 1/3 power. Or another thing we could just do is raise both sides to the negative 1 power, which is notation for the reciprocal. If you raise the left side to the negative 1 power and multiply by the exponent of negative 3, I'm going to get b cubed. And on the right-hand side, if we raise 1/3 to the negative 1 power, that's just notation for the reciprocal. I get positive 3. This tells me that my base must be the cube root of 3. Okay. So, final answer, remember a was negative 3, d was 8, and we just found the base was the cube root of 3. So f of x would equal negative 3 times the cube root of 3, that's going to be my base, to the x power plus 8. Okay, and there is my final answer. Okay, now that was a funky base, and not quite sure, I was hoping that there'd be a better point on the graph that actually went through where 2 grid lines met. But this should give you the general idea of this process that you would go through to find the form of a transformed function using its graph. Okay, so I'll stop there. Thanks for tuning in. Keep this video short. We'll talk to you guys later. Have a good one. Take care.